Hi, everybody. I'm Konstantin. I'm going to talk about message in a bottle. But before I start, I wanted to thank Engineered who are sponsoring my talk here. They're basically paying for a trip and hotel. So without them, I wouldn't be here right now. So thanks, Engineered. And yes, as I said, I'm Konstantin. I'm on GitHub, RKH. I have this extremely long Twitter handle. It's probably easier to go to my blog and click on Twitter than to type that, in case you want to follow me or just check out my stream or something. I'm currently a student. I just graduated at that Haase Plattner Institute down there. That's in Germany, near Berlin, and I'm going back there to continue with my master's program this year. I'm currently the maintainer of Sinatra. I don't know if you guys have heard of it, but it's quite handy. And together with Alan Harris, I'm also working on a book about Sinatra, which is supposed to be released rather soon. I'm a member of the Reg Core team, and I'm currently working on Rubinius together with Brian Ford from Portland, and that's an internship sponsored again by Engineered. Okay. In this talk, I want to go into detail what's going on under the hood, what makes Ruby tick, how do those Ruby implementations actually run Ruby. Yes. Well, here's the knowledge I'm going to drop. 1.8 is slow because it's interpreted. And surprise, surprise, so is 1.9. OK, that was my talk. Thanks. I'm just kidding. So Ruby, right? And message in bottles. If you haven't figured it out, the message in the bottle is actually a metaphor for sending a method call to an object, and that's what I'm going to talk about. There will be a lot of code in this presentation, and I try to make sure that I don't lose anyone. Feel free to ask questions right away rather than at the end. Yes? Thanks. So for some reason, there are a lot of Ruby implementations out there. I counted 58, or actually 56, because or maybe 55, depending on what you count as an implementation. However, I'm going to focus on the three large ones, JRuby, MRI, 1.9, and Rubinius. And here's a short overview. I'll talk about the method dispatch and execution while looking at MRI, and I'm talking about inline caches and jitting while talking about Rubinius. And I'll talk about Invoked Dynamic while talking about JRuby. That doesn't mean that only those implementations do that. OK, only JRuby is doing Invoked Dynamic, but both Rubinius and JRuby have a JIT, for instance. I had some help for this talk from Koichi and a lot of help from Brian and also from Charles Nutter. All those three guys are rather active in the specific Ruby implementations, and all those three guys are here, so buy them a beer or something. OK. This is what I'm going to talk about, 42, just for the example. So to make sure you all have an idea what I'm talking about, most of the examples will be talking about this code, specifically about what happens at this point if we call this method. It's basically just checking if the value is 42. You can pass in a string and an integer. Well, all the Ruby implementations, you're not supposed to understand all that right now, but all the Ruby implementations compile to bytecode, and the basic idea of my talk is to start from the bytecode and then look at what's going on there. That's the bytecode, or somewhat the bytecode for value 2s for MRI, Rubinius, and JRuby. Or JRuby you can get different bytecode, but I come to that. So the plan is, if you want to execute some Ruby code, some method call, you first have to search for the method, and then you have to execute the method. But you also want to have that fast. So how do we get that fast? Well, we search faster, and we execute faster. It's easy, right? Okay, we're done. But how do we search faster? The first thing we can do is, or one thing we can do is inline caches. I'll explain that, which is basically in the code, store where we're going. Then lookup caches, which is at the object, store, or at the class, store where to find methods that are inherited. And we can do inlining to avoid a lookup or a method call, like add all. And we can speed up the execution by reducing the operations. I think MRI is about to do that. Like, instead of having one operation that does one thing, have one operation that does three things, so you don't have to have three opcodes after each other. You can do just-in-time compilation to machine code. You can do inlining, and, well, you can speed up search, because then your execution is faster, because the main part of the execution is just looking for methods. All right, MRI. So if you call a method in MRI, there are different ways, but basically, almost always, you end up in a C method called RB_call0. That's the method. And what is important about this method is, here's the search. Oh, no, I'm sorry, I'm on the wrong. Here's the search. And here's the execute, just like I promised you. Okay, now how does the search work? Well, did I say there's a lot of code in the slides? It's basically the, oh, dang, I messed up. It's basically the method dispatch we're all used to. Just start from the class of the object, go through all the superclasses here, and check if the method exists. Well, and superclasses in that case also included modules, or I classes, how they're called in MRI. Well, and that's a basic dispatch. Now that we have the method, all we have to do is execute that method. This is done by this method. You don't have to get all that. I just wanted to show you, like, I always put like comments where important stuff is. Here it's actually going to execute whatever the state of the current context is. What that does is an extremely long method where I couldn't find important parts to tell you from, but basically it goes to there's an instructions.def file where all the for every bytecode there is a chunk of code that will be executed when MRI or YARV in that case is interpreting the bytecode, and that looks like this. Oh, I always mess this up. I'm sorry, I have the new show off with the presenter view, and I'm not used to that. So I just wanted to show you the code that you get a feel of how the implementations look like. This is basically the code for the bytecode for sending a method, and it's taking some arguments from the stack, and basically down here it's calling the method, which will again get you to the method dispatch I just showed. Okay, so that was a lot of code. Let's talk about Rubinius. Well, in Rubinius, you have basically this structure, which is similar to what all the Ruby implementations have. So every module, and the module is the superclass of class, and included module has a method table, which is basically like a hash, but more low-level construct you can easier access from C++. And for every method, there is a bucket, which has some metadata, and it references to a compiled method, which is basically the bytecode representation of a method. And the fun thing about Rubinius is that you can actually play with that from within Ruby. And this is basically the same lookup logic I showed you, just implemented in Ruby. Note that we have to use direct superclass down there to make sure we're also dispatching through all the included modules. And if you get hold of that method object, that compiled method object, you can do some fun things with that. But first we have to get hold of it with the lookup method, and then that will only give us the bucket. So we have to ask for the compiled method, and we'll return a compiled method object. And we can decode that to take a look at the bytecode. We can also get the opcodes, which is more like the decode display is more like semantic names you can understand. And this is what is actually stored in memory or on file if you save the compiled output on file. And it's referencing literals in there. I'll come to that on the next slide, that are stored in the literals tuple. Tuple is kind of like a fixed size array. Okay, let's try to figure out what this does. So in the literals tuple, there's 2s, 42, and equal. And we also have locals that are used in there, which is value, which in our case is 42. And then we have this tuple of bytes that are the method. If you take a close look at those, we start off with the bytecode for pushing a local onto the stack. This back here is the stack. So we have 42 on the stack. Then this is the bytecode for sending a method, which basically takes 2 arguments. The first argument is the index of the method name in the literals tuple. Up here, 2s has the index 0. And the second one is the number of arguments, which is 0. And then we have the string 42 on the stack. After that, we push the literal with the index 1 onto the stack, which is 42. So we have 2 times 42 on the stack. And then Rubinius has to duplicate that, since if it doesn't and someone calls, for instance, G's up bang on that string, then this will be modified if you replace it, for instance, with 55, and next time you have to pass 55 to the method to get it to return true, which actually works. If you go on GitHub on the repository, I have a fun script there which modifies the literals. And after that, it's sending equal, which has a special bytecode, so it can do some optimizations. And we have to return, since on bytecode level, there's no implicit return. Okay, so we want to get inline caches into that, so we don't have to have a lookup whenever it's doing the send stack, because you remember I told you I was talking about this 2s mainly. So what Rubinius does, it takes the bytecode and replaces the 2s call with an inline cache object. If you don't believe me, here's the code. Or at least the code which is using it as an inline cache object. This is basically, again, from the opcodes definition from the instructions.def from Rubinius. And this is, like I showed you before, the send bytecode. I mainly put that in here because in my talk description I said I'm going to have C++ code. And I made my slides and figured I don't have C++ code. So I figured let's put that slide in there. C++, ladies and gentlemen. Okay. The inline cache actually has a reference to something called the VM method. And the compiled method also has this reference. So this is for instance, the inline cache in this example would be referencing the VM method of 2s. Now, the fun thing is that the inline cache can actually, during its lifetime, change what method it is referring to, or basically anything. Oh yeah, first of all, the caching part is that VM method is already referencing the 2s code. So it doesn't, once the lookup is done and it's in the inline cache, it doesn't have to do the lookup again when visiting that point in the bytecode, unless the type changed. So there's a simple check where it checks that nothing has changed. If someone defined 2s, then it will do the lookup again. Or if that's a different class that's coming in there, it will do the lookup again. But if nothing changed, then it will use that method. And yeah, it can run that method. And as you can kind of see there, you can specialize, you can change such a VM method. But why would you do that? Well, the standard version of such a method is just have the bytecode stored in there and execute that bytecode with the VM, basically interpret that bytecode. But that isn't fun. Yeah, that isn't really fun, except for you don't have to do a lookup. You can actually have bytecode with breakpoints in there, which has the advantage of you can run a debugger and it will only slow down the method where you have set a breakpoint. That's why Rubinius can do debugging without slowing down the Ruby program, which MRI can't. And you can specialize for arguments, like doing some optimization if that's a string you get in there, whatever. That's currently under development, I think. And last but not least, you can JIT that code. That means you can actually, instead of referencing bytecode you will interpret, you can reference machine code that will, well, run directly on your CPU. And it works like this. You take the Rubinius bytecode. Rubinius translates that into the immediate representation for LLVM, and then let's just LLVM figure out how to compile that to native code. It does all the inlining optimization stuff that LLVM is known for. And that way speeds up execution. All right. Any questions so far? No. Yes?
So does Rubinius do any sort of analysis on what it's doing, sort of like the JVM hotspot?
Yes. So the inline cache tracks how often it's called. It tracks if there's always the same coming in. And there's a heat. And basically, if you call the method once, then the heat value is increased by 1. If the method does a loop, then the heat value is increased by 1. And I think it's something about if it hits 4,000 or something, then it will compile it to native code. Because basically, if you just execute the method once or twice, it's way more expensive to compile it than to just interpret it.
Does it try, so it's doing that at runtime?
It's doing that at runtime, just like a hotspot. Okay, and JRuby is basically doing this something similar, because that's why it's using the JVM, amongst other things. JVM is known for doing that well. Okay, so let's talk about JRuby. And lately, if people talk about JRuby and about performance and about method dispatch, what they talk about is Invoked Dynamic. Okay, but there's a lot of buzz about it, and do you guys think you know what it's doing? No. All right, then let's try to figure that out. So there are two different kinds of bytecodes. The current JVM trunk master it's Git, so it's master. The current master can produce, depending on what JVM version you're on. The one is the one you also get with the older JRuby versions, which is using invoke virtual and a custom call site object. Well, Invoked Dynamic is using a custom call site object too, but and the new one is using Invoked Dynamic. This is again the extract from the method I showed you at the beginning that is calling to S. So invoke virtual is the normal method bytecode invocation for the JVM, and invoke dynamic is the new hot thing they added. Let's take a look at those. Invoke virtual looks like this. It uses the custom runtime call site, which actually encodes the dispatch logic for JRuby. And whenever you come across that point, it will go to that call site and say, hey, I want to call that JRuby method. And it hands 3 arguments. If you don't send any arguments, the one is the thread context it's running in, the next is the caller, and the third one is the receiver, and then it returns, again, a Ruby object, as you would expect. The fun thing is about Invoked Dynamic, you could actually put any name you want, you don't see that, at where the call is, and Invoked Dynamic would be able to resolve that name, or your logic would be able to do that. But what JRuby is doing instead at the moment, I was told that that will change, might change. It's using call just as an identifier, whatever, and pushes the method name onto the stack. So it will actually be passed as argument to the method. And yeah, again, it returns a Ruby object. But with only that, the JVM would not know what to do. So there's a signature down here, which looks like this. Fun. Okay, so there is in JRuby this invocation linker, which is taking care of setting up Invoked Dynamic properly. And the important thing about that linker is it has a bootstrap method and a fallback method, and it returns a call site. And that call site is like the inline cache in Rubinius. It will be placed at that point. So it's kind of like that inline cache in Rubinius, and it will be placed at that point in the bytecode. And how it's supposed to be used is in the bootstrap, search for the method with your method lookup logic and place it there. And if that fails, or if a guard fails, you can place a guard in front of it, then please call the fallback method. Now, the interesting thing about the bootstrap in JRuby is that it's not looking for the method like at all, because it doesn't know what argument will be passed as the method name. So all it does is place a call site there that will, on the first call the fallback. So independent of whatever. So there's no lookup logic in here. And then in the fallback, there's actually the lookup logic. The lookup logic is search with cache here. And if it doesn't find it, it has to place a method missing in there. And then it is actually updating the call site to point to that method it has found, and then calls the method. So all the JVM optimizations can start from the second time you visit that point in the bytecode, or I don't know, probably happen whenever you place it there. And then the JVM can do all those inlining, hotspotting, and so on way easier because it's treated equally or somewhat equally to a normal JVM method call. Oh, yes. I kind of rushed through that, did I? Yes. That was it. Oh, wow. Man, I'm really sorry for rushing through that because I don't know, I have this new presenter view from show off, and it indicates the color here, and I was under the impression that I have time issues. Okay, should I explain something more in detail? Because I was going through a lot of code in not that much time, I think. Yes.
I have a specific question about the JVM or about the JRuby. So the difference between invoked virtual and invoked dynamic, it sounds like what you said invoked dynamic does is the first time it tries to call a method, it automatically fails and has to do a lookup.
No, that's so the first time it visits a bytecode, the bootstrap will be called to find the method that should be placed there. That it's going to the fallback is specific to the implementation JRuby is using, because the issue is in the bootstrap, you do not actually have the arguments, you only have the classes of the arguments passed to it. Because the JVM, as Java works, the lookup and the method signatures, that's all based on the number and the classes of the arguments. So that's what it uses as kind of key to fill up the caches and key for doing inlining. So with Invoked Dynamic, you basically have to map it onto those signatures for dispatches that do not work in that way.
What expires the caches? Are there
so there are guards. I think both Rubinius and JRuby are down to actually one single check for a normal method dispatch, which is basically a true-false. If it returns true, then everything's still fine, and if it returns false, then we have to do it all over again. And it's basically like a number checksum thing, where if someone defines a new method, that value changes, and then that value changes for that class, and then it will be invalidated. Yes?
In your opinion, what's the number one thing that MRI could add or change
To what? Become faster?
to make it faster or better?
Yeah, code adding JIT, for instance. So what MRI is doing is trying to add super instructions. If you have, like, in the bytecode, up here, if you have, I'm always on the wrong side. If you have get local and send, then it has to go through the VM loop 2 times. And what they are trying to do is, for some cases, for instance, in that case, you could do a get local and send opcode. You would only have one opcode and encode all the logic in there. The issue with that is that you will not, you're not able to change the class of complexity. So if you double the number of opcodes, the best thing you can do is cut the performance, the time it needs in half, but that's not realistic. So it will only scale linear. It will not change the performance overall. Whereas jitting and inlining can actually change it overall, because you enable a new, much bigger world of optimizations, and even the CPU engineering people can help you run your stuff faster, basically. So that would be one thing, I think. Yes.
I saw on the Rubinius slide that it was a duplicate string.
Yes.
That seems like it has the potential to add a lot of overhead. Do you have any idea?
Okay, so the thing is,
All of the implementations do constrain.
yes, you have to. Let me show that. Because the string in the literals tuple is actually one string, and if you hand out the same string always and someone modifies it, then it will be modified for all this. It might be easier to understand if you take a look at this. Yes. So I load the example code, go to the literals tuple of the method and place 55 in there, and all of a sudden 55 is the ultimate answer. And if you would not duplicate that string, then anyone could take that string that it's handed to from the method and do replace, pass 55 to it, and then you could do really evil things by accident.
If we had mutable strings, we wouldn't have to do it unless it's mutable. And
Yeah.
Ruby strings in the literal table.
Yeah. So you don't have to do that with symbols because you can modify those. Did that answer your question?
Yeah.
Oh, okay.
So try and use symbols where possible.
Yeah, but the bad thing about symbols is that they are not garbage collected. So if you use, for instance, symbols for user-generated data or something, then it will just fill up your memory and they'll never go away. Feel free to ask more. Okay, you don't want to? Yes. I think we have a lot of time for discussion.
Why are symbols not garbage collected?
Because that's what Ruby does. Because symbols are supposed to be, it's way cheaper and they're used for like the method handles for interning, and also if they're garbage collected, then they would be created all over. And basically all the literals. So if you define that method in Rubinius, for instance, that string 42 is never garbage collected because it's referenced by that method. So it will only be garbage collected if the method is garbage collected. And it would extremely complicate literals, for instance, if you would garbage collect symbols. But you might want to talk to Dana. Oh yeah, Charles.
Well, the big thing is that symbols all have to be the same object everywhere. So you have to have a reference to it somewhere. You can't create a new symbol or it won't be the same object in memory.
Yes.
Some languages, some Lisps, for example, do have a function called uninterned, so you can remove like user-generated symbols, but it does not make sense to do it for program codes.
Yes, there was another question back there.
Yeah, I was gonna throw you a nice meatball here, just hit it all apart. But if somebody were interested in trying to understand and piece together or explore these virtual machines, like you've done in this study, how did you approach this?
I grabbed the hold of Brian Ford and told him explain that to me from Rubinius.
I mean, is there a particular, say, class, C file, a starting point?
Yes, if you're in, depends on what you want to look at. So I found for myself that both the Rubinius code and the JRuby code is pretty easy to read, but it's a ton of code. If you go into the CRuby code, it depends on where you go. I would recommend starting with the search method because that's small code. It's pretty understandable. All the related methods are right below it, which is not always the case with the other methods. And then, okay, what I mean by hard to understand is wow. This is actually from the VM methods, so they all have pretty complex workflow. And this doesn't have the most complex workflow, but still it has the pattern of having a label in front of a switch. And that switch is nested. There are more switches in that switch. And from time to time it says go to again. And that is just, might make sense, but it's really hard to understand if you just want to follow the program flow. And yeah, I had the advantage of just asking Koichi about that code or something. Yes, and there's the dog picture. Any more questions? Yes, over there again.
Do you think there's any chance or any possibility that the entire state of the execution stack could be serialized for any of these? I don't believe any implementation Ruby supports that right now.
Maglev does, kind of, because it's image-based. Apart from that, no proper Ruby implementation supports that. I'm not sure if that's hard or anything. Feel free to talk to all the people that are here. And make sure I'm with you, because I know that there have been discussion about this from time to time, but there's no implementation on any other apart from Maglev. The Maglev people are over there. Okay. Then, in that case, thank you all for listening to my talk.